Hey everyone, I just wanted to record a short video to help out with one of the most common problems I was seeing with the exam number 2. Mostly on the second problem, the first problem dealing with induction, where I asked you to prove by induction that a certain summation formula was true, but it's also something that pops up on a couple of the other problems involving induction and in other work I've seen you all turn in. So it has to do with the way we kind of write things out when we're trying to prove a particular equality. Just want to make sure that you're aware of what you're saying, what you're really saying when you mean to be saying something else. So the common problem goes something like this. Remember in problem number 2, so this is exam 2, problem number 2, and hopefully this will be useful as you do your revisions, which are due this Friday as well. So I hope you get a chance to look at this video. I'll send you an email about it. So exam 2, problem number 2, asks you to prove a particular formula. Namely that if you take the sum of the first n squares, then you get, honestly, I'm not sure I remember the formula here, then you get a particular formula that you can use as a closed form that just expresses that sum in a succinct, explicit way. So most people got at least partial credit, if not full credit on this one. A lot of folks had the right idea, had a good base case, inductive hypothesis, inductive step. The structure was there, the idea was there. The one thing that a lot of folks struggled with was just in the base case expressing exactly what you mean to say when you're writing down. So in the base case, for instance, which is the case n equals 1, we want to prove, or we want to show, that 1 squared, the left-hand side of the equation, when we plug in n equals 1, right, our sum stops at 1 squared and it begins at 1 squared, that 1 squared equals, now we plug in 1 for n on the other side as well. 1 squared should equal this. Notice what I've done is I've written out the words we want to show. A common mistake would be to write something like this, but that is what we're trying to show. Again, making it clear with the English language explanation here allows the reader to look at this and say, oh, you're not assuming this equation is true, you want to show that equation is true. If you don't have that language, it's almost like, imagine that that language wasn't there, it's almost like you're just claiming to the reader that this equation is true, when we don't know that it's true yet. In fact, that's exactly what we're trying to show in the base case. So having language like this is really important. Now you can't write that. You can write, we want to show, so let's pretend that language is there again. We can start this off by saying we want to show that 1 squared equals blah, blah, blah on the other side. And there are a couple of ways to proceed from here. One way is to make use of this symbol, which is generated, I know we've seen this in class before. This is generated by doing, in LaTeX, backslash left right arrow with a capital L. You can use that symbol because it denotes logical equivalence. What I'm about to write down is an equality that is logically equivalent to this one. And what I can do is I can just simplify the left-hand side, right? And I'll simplify the right-hand side. I get 1 times 2 times, this works out to be 2 plus 1 is 3 divided by 6. And I can continue with another logical equivalence. Of course, this is going to be 1 times 2 times 3 is just 6 divided by 6 equals 1, which is true. Now, including that language at the end is sort of a cue to the reader that we've obtained a really obvious logically obvious result here. And the logical equivalence of this equation with this one, and in turn this one, is what enables us to conclude that the original equality that we wanted to show is in fact true because it's logically equivalent to an obviously true one. Does that make sense? So that's one way to handle it. But we do have to, if we're going to do it this way, you need to make sure that you've got these sorts of connectors that show what the relationship between two successive lines is. And you got to have language like this at the end and at the beginning to sort of contextualize what's going on. If I didn't have that language and I didn't have these connectors, you would have a chain of equalities that really don't tell us what's going on. It almost looks, again, like you're claiming this is true without any proof, which is not what we're after. What we're after is trying to show that this is true. And we do that by showing in a couple of steps that it's logically equivalent to something that is obviously true. So this is one way we can handle this. Another way we can handle this, and notice that this is really an equation of the form left-hand side equals right-hand side. And you can, in general, one way to do this is to reduce it to an obviously true statement doing a succession of logical equivalences. Another way to do it, and I find in this case is almost easier, is to say, so as another way, we could simply begin with the left-hand side. The left-hand side in this case equals, well, in this case, I don't think I want to begin with the left-hand side because it's a little, it's pretty obvious what the left-hand side is. The right-hand side is the one that requires a little more work. So the right-hand side in this case is going to be n times m plus 1 times 2m plus 1 over 6. And now we plug in n equals 1, and we see in that case 1 times 2 times 3 over 6, which reduces to 1. And now we notice, hey, that's really just 1 squared, which is the left-hand side. So in this case, instead of working with the whole equality, where I took both sides of the equality and I simplified them until I got an obvious equality, what I did here is I started with just one side of the equality. Typically, you start with the one that can be reduced the most, the one that's the least obvious, and you reduce, reduce, reduce until you get the other side. This comes up, excuse me, this comes up also in the inductive step for this problem, and also in problems number 4 and 5 in the exam. You want to make sure you're using one of these two structures, right? Either reducing both sides at each step, making sure that you're clear about the logical equivalence, or working with a chain of equalities, starting with one side and ending with the other. You may go from left-hand side to right-hand side sometimes, again, depending on which one's more complicated. But one of these two methods is really necessary. Let me just end with another common mistake some folks were making. They tried to do something like this, but notice the structure of this proof is to start with one side and end with the other, because those are the things you're trying to show are equal to each other. Another common mistake people would make, this is the right way, another common mistake people would make would be to write down, it's almost like they're starting with the equation left-hand side equals right-hand side, like that's what you want to show, so you're starting there, but you're not saying explicitly that's what we want to show. And then people would simplify the right-hand side, and they would just assume that, well, that shows that the left-hand side is equal to the right-hand side if you end up this equaling 1. But because the left-hand side isn't written at the end where it should be, it's not this form. What they have was something like left-hand side equals right-hand side, and they reduce to 1. Well, that's great. They both reduce to 1, but that doesn't expressly show that they're equal to each other. It's only if you go from one to the other with a chain of valid algebra in between that you could show that the two are equal to each other as desired. So I hope that helps. Again, the two ways that you can do this in general are starting with one side, going to the other, or working with logically equivalent equations, starting with the one you want to show and reducing it to one that is obviously true. Please send me an email or drop in the office hours for class. I've still got those going on from 9 to 10 on Mondays and Wednesdays through the final exam period. So I'll have those for a couple more weeks now. If you have any questions, get in touch with me, and I'm happy to help out. Thank you so much.